The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Okay, so as Mike told you, I'm going to be talking about live load testing and long-term monitoring of the Varina Enon Bridge near Richmond, Virginia. I'd like to acknowledge my co-authors, Mark McGuire, who is an assistant professor at Utah State University, and Tommy Cousins, who was my colleague at Virginia Tech for quite a while but moved to Clemson University about a year ago, and also the sponsor of the project, which was, at the time, the Virginia Center for Transportation, Innovation, and Research, but has now reverted back to the Virginia Transportation Research Council. So today I'll first give you some background information on the Varina Enon Bridge and the distress that was observed during a routine inspection that sort of was the impetus for us doing this live load testing and monitoring. Then I'll present the live load results in comparison to some simple models, and then some of the results from our long-term monitoring of about 1 year of the data. So this is the Varina Enon Bridge. The main spans are cable-stayed structure. The approaches are span-by-span constructed segmental box girder units. It was designed by, at the time, Fig and Mueller back in 1985, and it was open to traffic in 1990. So the area of interest of our research was actually the approach structure. This is on the northbound side of the bridge, the southernmost approach unit. It has 6 150-foot spans. Again, they were erected using span-by-span techniques with exclusively external post-tensioning. And the distress was noted by inspectors during a routine but detailed inspection in the summer of 2012. One of the locations where they saw this distress was in span 6, about 3/10 of the span length away from the first interior pier. And what they saw was that the joint between segment 2 and segment 3 in that span was opening under traffic. By just their visual estimate, they reported that it was opening a 1/16 of an inch repeatedly under traffic loads. There was also some distress noted in span 5, near the midspan in segment 4, and this distress was actually within the segment rather than at a joint, and they noted flexural cracking and then also this diagonal crack across the bottom. So this led to us having discussions with VDOT to do some live load testing. They had also hired Parsons Brinkerhoff to do some more detailed analysis of the structure to determine if this was really a major problem or an anomaly or what was going on. So our testing we did with 2 lowboy tractor trailers, one of them weighing about 101 kips, the other one about 114, and both of them had closely spaced rear axles that were around 60 kips. We laid out some truck crossing paths. We actually had the shoulder and the right lane were closed to traffic for our equipment and work. We had 2 trucks that were parked on the shoulder, a snooper and a moog, to help us place our instrumentation. And so the truck crossings, one we rolled the trucks right across the center span, one we rolled a single truck across this left span, and then the third load case we rolled the trucks side by side in the adjacent spans. To determine if our data made any sense, we did a very simplified beamline analysis. This is the cross-section of the approach spans, almost 58 feet wide, 18 feet at the bottom of the box, 12 feet deep. We threw in everything but the kitchen sink in estimating a stiffness. So it had the concrete box plus the 2-inch overlay plus the barrier rails plus transformed cross-sections of the rebar and the tendons. And this gave us the cross-sectional area in the moment of inertia that we used in our comparison analysis. And we found that the comparison was pretty good. Again, load case 1 and load case 2, each load case we ran the trucks 2 times to make sure that our data was consistent. And our calculated deflections in each case within 1/1000th of an inch here, a couple thousandths of an inch there, and actually, believe it or not, spot on for the double load case. We also looked at some of the strain gauges that we had placed through the depth of the cross-section. We had them at the midspan of span 5, we had them near the first interior support, and we had them at the 0.4 L position on the exterior span. And with these plots, I'm comparing 4 different incidences. The 2 truck load case, maximum positive and maximum negative moment at that location, and then the one truckload case, maximum positive and maximum negative strains at that location. And so in each case, the dotted line is always the analysis, and the solid line with the dots is the measurement. And so we got pretty good results, especially with the upper gauges. The bottom slab gauge, again, was a little different, which could be related to the proximity to the cracks. This is at the support where there was no cracking, and you can see, again, comparing the dashed line, which in each case is the analysis, and the solid line, which is the measurements. There we got very good correlation to the measurements. This is near the opening joint, and again, we got decent correlation near the top, but things were a little off at the bottom of the slab because, at least our assumption is, it's always instrument failure, but we believe it was due to the proximity to the joint. So a recap of the live load test. The visual estimate by the inspectors was that it was opening a 1/16 of an inch under traffic, but I do want to note this was measured on June the 29th of 2012. We looked at the weather station data from the airport, which is not too far from the bridge. On that day, it was 103 degrees Fahrenheit. Meanwhile, the day that we tested the bridge, we only got a joint opening of about a 1/64 of an inch, even with those two trucks of over 100,000 pounds each. But that was performed on August 12th of 2012, and the temperature at the time of testing was only in the 80s. So this led us to believe that the excessive opening on the day that the inspectors were there was due to thermal gradient issues. And so we established a long-term monitoring program to try to investigate that hypothesis. So we instrumented very close to the joint that opened. Again, it's between segment 2 and segment 3 on span 6. And at that location, we put LVDTs across the joint to measure the joint opening. We also put thermocouples throughout the cross section so we could get an understanding of what the thermal gradients were. And then we also had a strain transducer immediately adjacent to the crack. We also put instruments at the 0.4 L of the end span, which should be the location of maximum moment under our truckloads. And we had a single strain gauge on the bottom slab there, and we used that as our triggering device. So we let the long-term data acquisition run at about 50 hertz, and every time that gauge registered a strain of over 12 microstrain, it would record all of the data for a couple of seconds before and after that strain event. So now if we look at the data that we collected from that triggered event between September of 2012 and September of 2013, we had 4,673 strain events that were over 12 microstrain, and this is our histogram. So again, most of them are pretty small, 12, 13, 14 microstrain, but we did have some all the way out to about 3 times our triggering level, so 34 microstrain. Of those total 4,673 strain events, only 290 of them resulted in a crack opening measured by those LVDTs of greater than 0.003, and the biggest one we ever saw was a 32nd of an inch. So we're still not to where the inspectors estimated the crack opening to be. But again, it was our opinion that that was because of the influence of the thermal gradient. And so we started looking at our data a little bit differently to try to sort out the influence of the thermal gradient. Again, recognizing the thermal gradient currently in AASHTO is a nonlinear gradient with a maximum differential between the top of the deck and the web of 41 degrees Fahrenheit, and it's nonlinear. The actual design of this bridge was done with a linear gradient with a maximum difference from top to bottom of the structure of 9 degrees Fahrenheit. So we're going to compare 2 different months of data. July of 2013, 534 strain events, 51 crack openings greater than 0.003. Typical maximum concrete temperature, top of the deck, was between 30 and 35 degrees Celsius. And the differential between the warmest location in the slab and the coolest location in the web was up to 16 or 18 degrees Celsius. We look at a different month, a cold month of December 2012, 277 strain events with no crack openings greater than 0.003, even though some of those strain events were pretty large. Typical concrete temperature down in the 5 to 10 degrees Celsius, and typical differentials only 2 to 4 degrees. So this is, again, just reinforcing our hypothesis that, yeah, that thermal gradient is making a big difference in whether or not the crack opens up. Another comparison, I'll drive you crazy with my comparisons. We're going to look at 2 events on the same day, same magnitude triggering event, but one of them in the morning, so this is when the differential is going to be the smallest. It was only 2.6 degrees Celsius. We had an 18 microstrain triggering event. The strain gauge at our crack measured a maximum of 4 microstrain, and we saw no evidence of the crack opening at all. Now we move to the same day. Now we're 3 o'clock in the afternoon. We have an almost 15 degrees Celsius differential. Same level of triggering event, 18 microstrain. And now this difference isn't much, but I want to talk about that. 6 microstrain, but we definitely see the crack opening to about 1/100th of an inch. And the interesting thing is we see this plateauing of the microstrain immediately adjacent to the crack. And you can see that that corresponds almost exactly to the opening and the closing of the crack. So once the crack opens, that strain isn't going to increase anymore because there can't be any additional tension transferred across the crack. Last comparison. This is all of our triggered events, and now we have the crack displacement on the vertical axis and the strain at the triggering location on the horizontal axis, and the dots are related to and this is actually the differential, not the maximum temperature at the top. So you can definitely see that when those temperature differentials are high, even a small strain event will make the crack open, but when the temperature differential is small, a very large strain event will cause no crack opening at all. And one more time, there's July, there's December. We decided that our hypothesis was good, but the next thing we really wanted to look at was why that joint? Why was it happening right there? So we did a simplified long-term analysis. This was built segmentally, span by span, and so the original system is different than the final system. So we did just a simplified analysis saying, well, the final distribution of moments within the system is going to be a weighted average of the initial moment distribution times e to the minus phi, where phi is our creep coefficient, plus the final configuration as if it had all been built in its final configuration from the start, times 1 times e to the minus phi. So again, if creep was 0, it would just stay in its initial configuration. If creep were infinite, it would creep all the way to its final configuration. If you use a creep coefficient of about 2.5, it's creeping about 90% of the way there. So I said, we'll keep it easy and we'll use the moment distribution from the final configuration. We also looked at the thermal gradient as currently presented in AASHTO, which again is a 41-degree differential between the hottest point in the top slab and the coolest point in the web. And so here are all of the different moments acting on the bridge. That's the dead load moment, again, final configuration. This is the post-tensioning moment, acting essentially opposite. These are the live load positive moment envelopes and negative moment envelopes based on the integer number of lanes on the bridge times the multiple presence factor. So that's a lot of trucks on the bridge. And here's the positive restraint moment from thermal gradients. So you can see it's twice the live load moment. So they're pretty significant. So if I sum them all up, this one is just dead load plus post-tensioning, which again is right around 0, which is awesome. Here I've added in the thermal gradient, so that bumps it up quite a bit. And here I've added in the positive live load moments. This is where our crack was opening at one of the higher points on this final moment diagram, and that's the point where the segment cracked. So led us to believe that, okay, so it makes sense that that was where we saw the distress in the structure. The remaining question, though, is, well, why not here and here and here and here and here? We don't know. But in summary, the maximum joint movement during the live load test was a 64th of an inch. That was less than what was observed by the inspectors. Maximum that we measured over the 1-year period was a 32nd of an inch, but again, we never saw a gradient as high as what we think was present on the day that the inspectors were on the job site. The thermal gradient is definitely affecting the severity and the frequency of the crack openings, and we're continuing to monitor and investigate this structure to learn some other things about the bridge, but to ensure that this type of crack opening is not going to be a long-term problem.